Okay, so hi everyone. Thank you very much for joining this week's seminar. And thank you very much to Malte for accommodating the change in time, which was a little bit of a surprise, but we made it work. Malte is a master student at LMU. I can never really pronounce the full name, but yeah, it's Ludwig Maximilians Universität München. And he's been working with Daniel Grun and Brendan O'Connor on follow-up of gravitational wave events using optical and infrared at the Wedelstein Observatory, which has a very fun story behind it. I mean, it has several fun stories behind it. I hope I'm not spoiling any part of your talk, Malte, but I just want to mention that the whole mountain belongs to the family that owns the company that makes the Uhu glue,
Oh,
and
I
this is
didn't know
their
that.
you what? Okay, no, so this is their hunting grounds. So if you go visit, which I had to go for a workshop, they make you sign a document saying that you will not go hunting on their grounds. Otherwise, they will take back the mountain from the university. So I had to restrain myself from, although there's not really a lot of wildlife. Anyway, so we're very happy to have you, Mate, to tell us about the curious case of EP 241021A. Take it away.
Yes, thanks a lot for the introduction. Yeah, I didn't know that the family is the same that owns the Uhu company. That's very interesting. And yeah, Wendelstein is also how I'd like to start, just to give you a bit of an overview of where I usually get the data I work with, and also where I go about once every month or two to observe myself. Here in the lower corner, I put a small map so that you can have a rough idea of where the observatory is located. It's about 60 kilometers southeast of Munich, at the northern edge of the Alps. And as you can see in the images, the view is absolutely amazing. And yeah, the observatory was first founded during the Second World War, actually, and it was used for solar observations because they wanted to examine if solar activity has an influence of the radio transmissivity of the upper atmosphere. But then shortly after the war, the observatory was taken over by LMU and is operated by LMU since then. For a long time, it was still used for solar observations, but then at some point the atmospheric conditions got too bad for that. And then in 1988, they built the first telescope up there. It was located here, but it was a smaller one. It was an 80 centimeter telescope. That was in operation until 2008, when they decommissioned that. And to be able to continue the educational operations, and they then put up this smaller dome right here and put a small 40 centimeter telescope in there to bridge the time during which this big 8-meter dome was built, which now houses our 2.1 meter Fraunhofer telescope. It's named after the somewhat famous lens maker Fraunhofer, who also discovered the Fraunhofer lines, because he was from Munich. And yeah, our telescope has an aperture of 2.1 meters with a focal ratio of about 7.4 at the Nesmith ports. So these ports on the sides here where our instruments are located. This gives us a pixel scale with our images of roughly 0.2 arcseconds per pixel, which is very nice for the location that we have to sample the PSF of the images. The three instruments that we mainly use on the telescope are, first of all, 3KK. It's short for 3-channel camera. And this is the instrument that I mostly use. It's very nice because it has 2 optical channels and 1 near-infrared channel that can all observe at the same time. So when I observe something, I immediately get color information and not just the magnitude in one filter band. And then, yeah, it has a relatively small field of view of about 7 arc minutes, but for what I am using it for, it's very suitable. Then we also have the wide field imager. And yeah, as the name might suggest, it has a bigger field of view. It's about 28 arc minutes, and it can observe the whole UGRID's Sloan filter suite. Then, last but not least, we also have a shell spectrograph. It has a resolution of roughly 60,000. And depending on how it's operated, it has 2 names. Either if it's just the spectrograph, it's called PHOTSIS, but also then we have a frequency comb that can be used for calibration, for wavelength calibration. And if it's used in this configuration, it's called MAPS, which is short for the Manfred-Hirt Planet Spectrograph. And Manfred-Hirt was the first director of the Wendelstein Observatory. Here on the picture, you can see the wide field imager on the left side of the telescope. The 3KK is located on the right. And this is also where the fiber pickoff for the spectrograph is located. If you have any further questions about that, I'm happy to answer them in the end. Now, I like to talk a bit about what I'm doing at the moment. So I use data from the Einstein probe satellite. It was launched in January last year by the main contributor to the mission is the Chinese Academy of Sciences. And Einstein probe is a wide field soft X-ray survey. And the very cool thing about it is that it has onboard trigger and real-time alerts. So they look with the wide field X-ray telescope, which are these square apertures here in the somewhat circle configuration, which observe a 3,600 square degrees field of view all the time. And they look for new sources popping up in these. This happens about 80 times per year, but also there's a significant flare star contamination, which they are getting better at filtering out, but still some come through sometimes. And here in this image, you can actually see the first transient that was ever observed by Einstein probe. Here we have a very bright foreground source. And in the upper right corner, there's a new source which was then designated EP240219A. 240219 is just the date. It's February 19th in 2024, and the A stands for that it was the first transient detected on that day. And yeah, one very interesting thing about these transients is that they are mostly not detected in gamma rays. So one initial idea was that these transients could be related to gamma ray bursts, but only some of them are, and some of them seem to be at least somewhat different from GRBs. And yeah, when they detect such a transients, they then slew the satellite to take a look with the follow-up X-ray telescope, which is called FXT. And yeah, that has a much better resolution and sensitivity. And yeah, allows us for a better localization of the source so that we know where to look. For what I will talk about later, it's also quite important that everyone has a rough understanding of how gamma ray bursts work. So I'd like to give you a short overview about that in here. So there are 2 types of gamma ray bursts, which are very creatively named short and long gamma ray bursts. Short gamma ray bursts are defined as lasting less than 2 seconds, and long gamma ray bursts is everything longer than 2 seconds. I will focus on long gamma ray bursts for now because this is what we need for later. And the hypothesis for how they are created is a collapsing massive star forming a black hole in the center, which then launches a jet. And so, yeah, this black hole is called the central engine. And now here in the animation, you can see the jet propagating outwards, and the jet is made up of material. And when shells in the jet collide, it creates internal shock waves, which release very high energy gamma ray radiation. This is what we then see as the gamma ray burst. But also the jet has an end, a front, and when this front of the jet hits the ambient medium around where the star was located, it creates a shock wave. It's a collisionless relativistic shock, so the radiation we see is synchrotron. It's not thermal, but nevertheless, yeah, this shock then radiates over the whole electromagnetic spectrum. So this is then called the afterglow because it's visible after the GRB for a couple of days usually, but sometimes also quite a bit longer. And yeah, it releases radiation from radio over the visible spectrum to X-rays and even high energy gamma rays. So everything can be observed in there. And for our characterization, these afterglows are actually pretty simple because they look like power laws. They look like power laws in frequency space. So the spectrum is usually just a power law in the visible. Sometimes there's also a break in the spectrum at other wavelengths, but it's a power law with one or two breaks. And then in time, the temporal evolution is a power law as well. So we just see a bright object, bright new object, and then when we watch it over time, we just see it decay with a power law. Yeah, that's most of what you need to know about gamma ray bursts for now. Now I'd like to tell you a bit about what I'm actually doing for my thesis. Yannis mentioned before that I work on a gravitational wave follow-up project. I've been working on that since 1.5 years now. But at the moment, it's more of a side project for me, which I only support a bit, and I mainly focus on the follow-up of fast X-ray transients that are detected by Einstein probe. We started this campaign in October 2024, and yeah, as already said, my supervisors are Daniel Grün at LMU and Brendan O'Connor at the Carnegie Mellon University in Pittsburgh. And our initial goal was just to understand the population of these new events because they have been observed in archival X-ray observations in the past, but then that had quite a long time delay, so people weren't really able to do follow-up observations of them and find optical counterparts or something of that sort. So now with Einstein probe, we are actually able to observe these events for the first time. And that's why we just wanted to observe as many events as possible and get an understanding of the population. We are still working on this, but for this talk, I'd like to focus on a very specific event because it showed a very interesting behavior over its evolution, and that is EP 241021A, which interestingly was the first event that we observed in this campaign. So we started out very lucky. And yeah, the X-ray burst was, as the name tells us, observed on October 21st, 2024. And the burst was detected by Einstein probe for about 100 seconds. And yeah, most importantly, it was not detected by gamma ray burst observatories that were observing at the time. It took quite long to identify the counterpart for this event. So the way this works is Einstein probe sends an alert to the astronomical community, and everyone who is interested can then point their telescope at the position they say that this first happened. And then people compare the images to archival images and do difference imaging and look for new sources. And by doing this, a counterpart was identified 1.8 days after the initial trigger. This is quite long. Usually it only takes a couple of hours. Yeah, later on, people discovered that there were some early observations where the counterpart is also visible. So the first detection of the counterpart was actually 1.2 days after the trigger. But yeah, this was the first one that was published. And then people also took a spectrum of the identified counterpart and determined that it was located at a redshift of 0.75. With Wendelstein, we started observing a bit later, even only 2.8 days after the trigger. We were a bit delayed due to weather, and also, as I already said, it was the first event we observed, so we had to figure out a bit of how exactly all of this works. But then over the evolution, we actually were able to follow the event for 40 days, and were able in this 40 days because then we had a period of very great weather, and we were able to take 22 epochs. So we observed it every day in the beginning and then every other day towards the end. And over this campaign, we totaled observing time of 38.1 hours. And here on the right, I have created a finding chart from all of these observations. And you can very clearly see the transient in the end. And the circles indicate the localization of the X-ray source that was detected after the trigger, so the X-ray afterglow. And yeah, we can see that the optical transient that was discovered is very much consistent with the Einstein probe and swift localization of the source. Notable is as well that up to this point, we were not able to detect a clear host. And we are hoping to change that when the position of this field rises again later this year. But yeah, unfortunately, up to this point, we weren't able to determine the host brightness, so our light curve actually may still contain some contamination from the host. So what was actually observed? This figure I took from the Xu et al. 2025 paper. This is the paper on this event by the Einstein probe collaboration. And here they show that they detected the burst for 91.9 seconds. And from the counts, from the count rate they detected during the burst, they determined the average flux to be about 3.3 times 10 to the minus 10 erg per centimeter squared and per second. And using this average flux and combining it with the duration of the burst and also with the redshift that was determined from the counterpart, we can estimate the so-called isotropic equivalent energy. So I showed you before the animation of a gamma ray burst. So in the gamma ray burst, we have a jet that then interacts with the medium, and we want to know the energy of this jet. Unfortunately, we don't really know how much of a portion of the jet we see. So what we can do is we assume that the jet isn't collimated, but it's isotropic and expands in every direction the same. And we can estimate the energy that the jet would have had if it was expanding over the entire 4 pi sphere. So this is very much an upper limit for the actual jet energy, but it gives us an estimate of the order of magnitude of the energy that was involved in the explosion that we observed. We can then combine this information with the spectrum that was observed by Einstein probe. The spectrum is well fit, as you can see here, by an absorbed power law with a photon index of 1.8. So yeah, the photon index is basically the slope of the power law. And yeah, what we can see here as well is some absorption features from hydrogen. And yeah, when we combine this, when we use this slope of the spectrum, we can definitely rule out that the radiation from the prompt emission that we see is of thermal origin, because at these energies, that would be much, much steeper. And also we can use this and combine it with the estimate of the energy of the explosion that we have. And by combining these, we can also rule out that the origin of the synchrotron radiation that we see is non-relativistic. So what we can know by just looking at the burst energy and the spectrum is we can tell that we probably saw some kind of at least mildly relativistic jet. And yeah, the most obvious contender for such a jet would be a gamma ray burst. So let's have a look if that actually could be what we have seen. So I think I mentioned it before. This jet was not observed by gamma rays, but since by gamma ray burst observatories, but since these observatories were active, we can determine some upper limits. So using the data from the CONUS wind mission, we can, depending on the assumed duration of the GRB, we can derive upper limits, which are plotted here. For reference, there are some short and long GRBs plotted, as well as so-called low luminosity GRBs. As you can tell, these are just GRBs with low luminosities. And now the question is our observations, are they consistent with the non-detection of gamma rays? So could there still have been a GRB that we just didn't see? Or can we rule out that there were gamma rays involved? For this, to determine this, we need to do a small excursion back to GRBs and take a look at the spectrum, because GRB spectra are usually quite simple. They are modeled by a so-called band function, which is basically just a broken power law. So you can see the first segment of the power law here, and the slope of this is determined by the so-called low energy power law index. And then we have also the high energy power law index. And also we know the peak energy, which is where the break is located. And the very nice thing is now, since we have, so we can make some assumptions on these slopes from just typical GRBs. And then we can extrapolate the energy that we saw in the X-ray band to the gamma ray band. And since we can characterize the spectrum by only these three parameters, of which two are assumed fixed, we can vary the peak energy to match the energy that we get from the bolometric correction of the isotropic equivalent energy in the X-rays, and can derive an upper limit for the peak energy with this if we also take into account the isotropic estimate of the isotropic equivalent energy. And this we can then use, we can plug this into the so-called Amati relation. It's an empirical correlation that was first described by Amati in the early 2000s. And they noticed that there is a very strong correlation between the isotropic equivalent energy of a gamma ray burst and the peak energy of the spectrum. And what we can see here is, depending on the time scale we use, so this is the 3-second upper limit, this is the 100-second upper limit, which would correspond to the duration of the X-ray burst. But actually, usually it has been observed that the GRB corresponding to an Einstein probe event is much shorter. So So we should focus on this lower time upper limit. And we can see that, yeah, overall, most GRBs, I mean, this sample is quite old, but the overall trend and sample is still representative. So we can see that most cosmological GRBs are actually at higher energies, and we probably should have observed them if they happen, but also from the, we know that the peak energy is lower than these, so we can tell that we probably observed some kind of low luminosity GRB, maybe, and it's, yeah, this would still be able to follow this relation very well, and is consistent with the non-detection in gamma rays. But of course, there could be other explanations. So yeah, one explanation would be that, yeah, we observed a low luminosity GRB and our detectors simply weren't sensitive enough. But other reasons that we didn't detect a GRB could also be that the burst just had a very low gamma ray efficiency. This can happen when the overall outflow has a quite low Lorentz factor, then not many gamma rays are formed. And another reason could be that we had a slightly off-axis viewing angle, so that the jet didn't point directly at us, but slightly away from us. And since the gamma rays are typically more collimated than the X-rays, it could be that we just saw the X-ray portion of the jet. And just to give you a bit of a comparison, here we can take a look at the figure from another PhD student from Italy. She also observed this event, and she took a look at the distribution of Einstein probe GRBs. So in her sample, she had the 88 fast X-ray transients that were observed to have a gamma ray burst counterpart. And 55 of them, so 17 of them have a GRB counterpart, and 55 of them had gamma ray coverage. So yeah, about 1/3 of the GRBs that had gamma ray coverage also were observed to have a GRB. And for the others, we can see an upper limit on the gamma ray energies down here. Now we can take a look at the ratio between the gamma ray flux and the X-ray flux of the FXTs that had gamma ray bursts, and we can see that they mostly fall between close to this line of a spectral slope of 1. But there are some outliers to harder spectra. What we can also see is that down here, we actually seem to have some very high energy X-ray transients. So they had a lot of flux in the X-rays, but no flux in the gamma rays. And this gives us, yeah, this tells us that these must have had very soft spectrum. So the SED falls off very steeply towards high energies. Possible explanations for this could be very, very high redshift GRBs, so that we basically see the high energy part of the GRB spectrum in the X-rays, and there are simply no gamma rays there because they have been redshifted to X-rays. It could also be that we are just viewing an off-axis jet in these cases, or that the jet was choked during the formation and couldn't properly form. Or maybe we are seeing some other very exotic types of explosions in the universe, which have not been characterized yet. Unfortunately, EP 241021A lies exactly in the overlap region between the gamma ray dark and gamma ray bright FXTs. So we can't really tell from this relation if 21A could have been a GRB or not. But this also very much gives us a constraint for the peak energy, because yeah, here we can see as well that the luminosity in gamma rays had to be quite small. So if there was a gamma ray burst involved, it would have had to have a very low peak energy. So much about the prompt emission. Now I'd also like to shortly talk about the afterglow. Here we take a quick look at the light curve in the X-rays. And what's very interesting here is that, first of all, in the beginning of the light curve, it seems to actually fall off rather, it's quite shallow compared to all these other GRBs that we can see in the background. This is not very uncommon for GRBs. Their plateaus of X-rays have been observed before. Unfortunately, I don't really have time to go into much detail about that. But we can see that the later decay of the light curve seems to match the overall slope of GRBs quite well. The only thing that's a bit different from what I told you about before is that here it very much looks like the energy seems more to be in the same ballpark as long GRBs and quite a lot higher by at least 1 order of magnitude from what has been observed for low luminosity GRBs. And now let's look at the maybe most exciting thing about this transience, the optical light curve. Yeah, here you can see all of the data we took with Wendelstein in the filled out circles. Yeah, we started observing at 2.8 days in the observer frame, which is the lower x-axis. And then the upper x-axis shows us the time since the trigger converted to the rest frame of the event. On the left here, we can see the apparent magnitude of the transient corrected for dust extinction in the Milky Way. And just for reference, on the right side, we can also indicate the absolute magnitude of the event. Overall, we can see that the decay seems to fit a power law quite well, which would be indicative of of a gamma ray burst afterglow, especially also since we can see this non-existent color evolution. So from our data, looks like the color of the transient actually was rather constant. And then obviously, what is very exciting, we can see this very, very steep rise here, which happened about 5.5 days after the initial trigger in the observer frame. And this is very hard to explain because it's very steep. So we only were able to determine a lower limit of the slope of this rise and to 3.5. So this is way steeper than everything that we know from typical GRBs. Also, one thing that we can note is that here in the R band, which is the blue light curve, the peak magnitude is about -21, but here we plot R plus 1, so it's actually -22. And this is what is typically seen for superluminous supernovae. So maybe it was a supernova that we saw here. But then when we consider the non-existent color evolution again, and also this very, very rapid rebrightening, we weren't able to reproduce the light curve by modeling it as a supernova. But then we discovered that actually there is a sample of GRBs, of GRB afterglows that show a similar rebrightening. And yeah, the main difference is that typically, so here we can see 21A and also 240414A, which showed a somewhat similar behavior. Compared to the light curve of other GRBs that had rebrightening. And we can see that GRBs typically seem to rebrighten a lot earlier in the evolution. So here it's on the order of 1 to a few days. But with GRBs, it's more usually more in the order of a few hundred seconds after the burst. But what we can see is that actually the slope of the rebrightening and also the flux ratio by which the light curve rebrightens seems to be quite consistent with what we see here. Another thing to note is also that here in the optical, the light curve, especially after the rebrightening, is also very much consistent with these typical long GRBs and way brighter than low luminosity GRBs, which is a bit confusing. But the main question is, what can cause such a behavior, such a rebrightening? And in order to give you an understanding of our explanation of this behavior, I'd like to return to this schematic of a GRB that I showed you before. So now we focus on the GRB afterglow up here. And typically what we assume is just that there is a shell of material that propagates outwards from the central engine and then creates the afterglow when it hits the surrounding medium. But now what could have happened is that the central engine didn't just release one shell of material, but multiple shells. And then these shells could have had different Lorentz factors, so that the outer shell, the faster shell, propagates outwards faster and clears out the medium in between. That's why we see nothing, no interaction of the second shell in this area. And then at some point, by the interaction with the ambient medium, gets slowed down. So when this happened, then the initially slower shell can catch up with the shock front and inject new energy into the afterglow and create this very steep rebrightening. And in the models we considered, the time scale of the rebrightening, so the very late point on time where it happened, can be explained if we assume that the overall Lorentz factors of the jets of the shells were quite low. But also, we are able to explain this very steep rise in the light curve, which is very hard to explain otherwise. One other potential explanation could be that we are seeing a jet with a very complex structure that interacted with the medium and created a reverse shock into the jet. And it could happen that this creates a light curve with two peaks if we see such a complex jet slightly off axis. But this exact scenario hasn't been modeled in enough detail yet to actually determine if it could match our observations or not. So that's why we think the refreshed shock scenario is the most likely explanation. And this leads me to the conclusion of my talk. We think that the prompt emission of the event that we observed can be explained by an at least moderately relativistic jet with a relatively low peak energy. The rebrightening of the afterglow could be explained by a discrete addition of new material at the forward shock front, so this refreshed shock. The only thing that still is a bit weird and that stands out is that the prompt emission seems to indicate a very quite low energy, comparatively low energy of the jet. And then the afterglow seems to imply the opposite and also is on the brighter end of GRBs that have been observed. So in order to understand the nature of what happened better, we would like a bigger sample size. That's why we keep observing and hope that we can see this behavior more often. For more details on what I've told you about, please have a look at our paper, which is on the archive. And there also were some other papers released about this event after we put ours on the archive, and they have some different interpretation of what happens. But unfortunately, I don't really have time to discuss this now. Yeah, with this, I am done and open for any questions.
Thank you very much. That was a nice talk, interesting. I see people clapping.
That's nice.
Do you, aside from clapping, do you also have a question? Please unmute yourself or raise your hand. Well, I can start with one. Meanwhile, people think about. Will be a naive question, but a jet that is reorienting or oriented more toward your direction, toward your line of sight, could give you the extra boost in luminosity of the afterglow that you are missing, or no?
I'm not sure if I understand what you're saying. So, I mean, in order for us to see the prompt emission, the jet has to be pointed at us. Because the radiation, so typically these jets have, are relativistic. So the irradiation that they release is beamed very strongly. So we can only observe the prompt emission basically if the jet is pointed at us.
Mm-hmm.
And yeah, but
what type of what range of viewing angle do you have an idea of what we are talking about when you say
it's a couple of degrees usually?
Okay.
I think.
Okay, I'm done. I was not aware of this. Okay.
Yeah, so the jet has an opening angle of a couple of degrees. Yeah, as I mentioned before, it could be that we are viewing this event slightly off axis, which could explain the non-detection of gamma rays. And also, yeah, it seems to be somewhat plausible that then a jet that has a more complex structure of this very simple model, that it has a uniform density and then is cut off at some point, could create some weird interaction with the surrounding medium, which then creates a reverse shock into the jet. So if I go back to this slide, maybe here at the edge, there is some interaction which then creates another shock that propagates inwards towards the jet.
Mm-hmm.
And that could also release more radiation and could be an explanation for the rebrightening that we observed. But we think that the injection of new material is the more likely and simpler explanation. But we can't rule out the other scenario.
Okay, but sorry, you said that the opening angle was 2 degrees, not the viewing angle, and that it's possible that you are observing.
Yes, but the opening angle and the viewing angle are actually the same, because the radiation is very highly beamed. So it's not an isotropic release of radiation. It's basically just in the direction of the jet. So this is very interesting because the viewing angle actually increases over time when the shock front decelerates. And this can then lead to a so-called jet break in the afterglow light curve, because typically in the beginning, we can only see a very small portion of the jet. So maybe only this region. And then as the jet slows down, the radiation from the jet becomes less beamed and the opening angle broadens. So the angle in which radiation is released broadens, and our viewing angle does as well. And then our viewing angle gets larger. And as long as we are still in our viewing angle only able to see the jet, it just decays with the power law. But then at some point it can happen that the opening angle becomes broader than the jet we are seeing. And then the power law decay actually becomes steeper, because then we also start to see regions of the jet that do not exist. And therefore, the radiation falls off more steeply. I'm not sure if that makes sense. I may be able to pull up a figure of that. I don't have a slide for that, but I have it somewhere.
I think I understood your explanation. I was just wondering how much this slight change in the axis, on axis, off axis, so a slight change in the viewing angle, if that can influence the boosting of the luminosity or not, as in the case as we see in
as far as
jet inactive galaxies, for example.
As far as I understand.
Yeah,
as far as I understand, it can't, but I'm also not 100% certain about that.
Probably here we are talking about a narrower jet also, and so more closer,
in the typical case,
to the tower.
Typically in the case of GRBs, the initial Lorentz factor is on the order of 100 or so, and then the viewing angle, so the beaming of the radiation, is the viewing angle in which we can see radiation, is proportional to, I think, 1 over the Lorentz factor.
Yeah.
So it's a very, very small angle that we can see the jet at in the beginning.
Okay. Thanks for the explanation. Are there any other questions? Don't be shy.
I can't hurt you. I'm a few hundred or 1,000 kilometers away.
I was wondering if you can say about the alternative explanations a bit.
Yes, so there were some quite weird explanations that we found. So other people also suggested that there could be a jet with a more complex structure and that this could be a case. But then there also were some other quite weird explanations from our point of view. So people suggested that it could be a recurring jetted TDE. So if we take a look here, let me share my screen again. If we take a look at the light curve again, what they basically said is, so they also used our some data from our light curve, and they said that there was some kind of TDE back here, then it decays, then at some point, so the orbit is complete and the interaction happens again, and this creates another bump in the light curve, and then they say that actually they see another bump in here in this small deviation from the overall decay. The only thing I find quite weird about this is, so there are some details that don't really fit. So this very late data points that we observe here do not really fit with their model. But also they say that it's basically a recurring jet, recurring TDE on a logarithmic timescale. And I wouldn't really know personally how that would happen, because the orbit timescale of the star that is torn apart by the black hole would to increase on a logarithmic timescale. And yeah, I just don't see how that works.
Okay. So I don't see any other raising hands. So thank you very much for your talk, for your time.
Thank you for the invitation.
And see you everyone next week. Bye everyone.
Bye.
Thank you. Bye.